Picture yourself standing on the top floor of a modern glass-wrapped skyscraper.
Oh, yeah. Super tall territory.
Right. And suddenly a massive wind event hits. Or, a seismic wave rolls through the bedrock.
You feel it immediately.
You really do. The floor beneath your feet actively shifts, and we aren't talking millimeters here.
No, not at all.
Hmm.
In some of these super talls, the lateral drift at the roof can be a couple of feet.
A couple of feet. The building leans, it flexes, it absorbs that kinetic energy, but crucially, it doesn't snap.
It's an incredible sensation, honestly, feeling that controlled drift. Because the architectural reality of these towers is that they are massive sails catching the wind.
We're giant pendulums in an earthquake.
Exactly. And if they were perfectly rigid, like if we designed them to not move at all, the internal stresses would be so catastrophic that the concrete would violently fracture.
Right. Brittleness is the absolute enemy of structural survival.
Exactly. The flex you feel is entirely engineered.
And the unsung hero of that engineered flex is hidden right beneath your feet and, well, right above the drop ceiling.
Yeah.
Today, we are tearing into the high-stakes world of high-rise structural design. Our mission for this deep dive is to dissect the evolution of coupling beams.
It's a fascinating topic.
It really is. We are going to look at why they are the absolute most critical members in reinforced concrete buildings and how the industry has arrived at the ultimate solution.
The plate reinforced composite coupling beam.
Right, the PRC beam. We have a huge stack of research to go through today, including the foundational design methodologies proposed by R.K.L.
A pioneer in this space for sure.
Definitely. And we are going to get into the raw mechanics of how these components are engineered.
Because the PRC beam is, honestly, arguably the most elegant solution to a massive structural bottleneck we've seen in decades.
Yeah, but to understand why embedding a steel plate inside concrete is so revolutionary, we have to kind of look at the global behavior of the building first.
Right. When you analyze a high-rise, the primary lateral resisting system, like the spine of the building, is almost always comprised of reinforced concrete shear walls.
These are just massive, heavily reinforced vertical elements.
Exactly. But an architect cannot hand a client a floor plan with solid, impenetrable concrete walls running right through the middle of the building.
Right, you need elevator lobbies, you need grand corridors, you need doorways.
So those massive shear walls get pierced, they get sliced vertically into separate, narrower segments, which we call wall piers.
And the moment you slice a shear wall into those isolated piers, you destroy its global flexural stiffness.
You do. They start acting like independent cantilevers, just swaying out of phase with each other.
Which is bad.
Very bad. To get that combined rigid body behavior back, you have to stitch those wall piers back together across the openings.
And you do that with coupling beams at every single floor level.
Right. I like to think of it this way. If the wall piers are the femurs and tibias, the coupling beams are the cartilage and the ligaments.
That is a great analogy. So when the building sways, the wall piers want to slide vertically past one another.
Exactly. And the coupling beams resist that vertical slip. They take on massive shear forces and massive bending moments.
And in doing so, they dissipate the seismic or wind energy.
Yeah. They are quite literally designed to take a beating so the primary gravity load-bearing walls do not.
And finding the right way to design that cartilage has been a total nightmare for the industry.
Oh, absolutely.
Because you need a beam that has incredibly high ductility, meaning it can yield and stretch and deform without losing its load-carrying capacity.
Right, but it also has to be something a construction crew can physically build hundreds of feet in the air.
So it's this huge battle between ductile performance and construction practicality.
That is the core conflict.
Yeah.
And if we track the history of how engineers have tried to solve this, you see this very clear evolution of failure and innovation.
Let's walk through those 5 historical contenders. For decades, the default was just the conventional reinforced concrete coupling beam.
Right. Just a standard rectangular concrete beam. You've got longitudinal rebar running top and bottom, and transverse shear hoops stirrups wrapping them.
And under static loads, or, in low seismic zones, they function perfectly well.
They do. But under high cyclic shears, stresses the kind generated by an earthquake slamming the building back and forth, their hysteresis behavior is highly problematic.
Yeah, let's unpack that hysteresis degradation. The research shows that with every cycle of the earthquake, the conventional beam's ability to absorb energy just plummets.
It does.
Why is that specific degradation happening at the micro level?
Well, it really comes down to aggregate interlock and diagonal tension. When the beam is subjected to intense shear, you get diagonal cracks forming across the concrete matrix.
Okay.
Under cyclic loading, those cracks open and close in both directions. So you end up creating an X pattern of intersecting cracks.
Oh, I see.
As this happens, the rough pieces of crushed concrete aggregate along those crack interfaces grind against each other.
Like sandpaper.
Exactly like that. And eventually, that aggregate interlock is completely ground down. The crack surfaces become smooth.
Wow. So at that point, the concrete is contributing almost nothing to the shear resistance.
Right. The vertical struts have to take all the load they yield, and you get a sudden, brittle, sliding shear failure right at the face of the wall pier.
And the sources highlight a very specific code limitation here. Conventional beams really only show acceptable performance if the nominal gross section shear stress is kept below a specific threshold.
Yes. 3 times the square root of the concrete's compressive strength.
Or 3 root F prime C in CSI.
Which is a severe limitation because the ACI 318 building code technically permits shear stresses up to 10 root F prime C for these beams.
Wait, really? The code allows up to 10?
It does. But the empirical research is overwhelming. If you push a conventional RC coupling beam past that lower threshold of 3, you're abandoning ductility.
It just becomes shear controlled rather than flexure controlled.
Exactly, leading to that catastrophic brittle failure we just discussed.
So the engineers hit a wall. They needed a beam that could handle massive cyclic shear without grinding itself to dust.
Right. Enter the innovation of the 1960s and 70s.
The diagonally reinforced concrete coupling beams.
This was a brilliant conceptual leap, honestly. Researchers looked at that intersecting X crack pattern and thought, what if we place the reinforcement exactly along the lines of the principal tension and compression stresses?
So instead of relying on horizontal bars and vertical hoops to handle shear indirectly, they bundled heavy longitudinal rebar and crossed them diagonally through the beam.
Right, creating an internal strut and tie model, an internal truss.
So the diagonal bars take the shear forces directly as axial tension and compression.
Exactly. The sliding shear failure at the wall interface is virtually eliminated because the diagonal bars are transferring the load directly into the core of the boundary elements.
That sounds perfect. From a pure performance standpoint, diagonally reinforced beams offer the highest ductility and the fattest, most stable hysteresis loops of any concrete member.
They are incredible energy dissipators.
But here the sources are brutal about the reality of these beams on a job site.
Oh, they're awful to build.
Yeah, the phrase construction practicality goes entirely out the window. Why do contractors hate these things so much?
Just think about the physical geometry of the rebar cage. You have your standard horizontal bars. You have heavy boundary confinement ties.
Okay, that's already a lot of steel.
Yeah, and now you're introducing 2 massive intersecting bundles of diagonal rebar. At the center of the beam, right where those diagonal bundles cross, the density of the steel is absurd.
It's basically a solid block of metal.
It practically is. And remember, you have to pour wet concrete through that.
And concrete isn't just liquid. It has large aggregate stones in it.
Exactly. If the gaps between the rebar are too small, the aggregate gets stuck, the cement paste drains away, and you are left with massive voids.
Honeycombing.
Right. Honeycombing right in the critical center of your beam.
So how did they try to fix that?
Well, to prevent it, the beam has to be significantly widened. A 14-inch width is the bare minimum, and 16 inches or more is standard, just to get a vibrator down into the formwork to consolidate the concrete.
And that leads right into the fatal geometric flaw of the diagonal beam, doesn't it? It's highly dependent on the span-to-depth ratio.
The aspect ratio is everything for a diagonal truss. The effectiveness of those diagonal bars relies entirely on the angle of inclination.
Okay, so if you have a short, deep beam, say a span-to-depth ratio of 1.0 or 1.5, the diagonal angle is steep.
Right, and it transfers vertical shear incredibly efficiently.
But modern architecture demands wide corridors, double doors, high ceilings.
Exactly. We frequently see architectural dimensions dictating a coupling beam span-to-depth ratio greater than 2.0, sometimes up to 4.0.
And as the beam gets longer and shallower, the angle of that internal X gets flatter and flatter.
Precisely. As that angle approaches horizontal, the vertical component of the force vector just approaches 0.
So the diagonal bars lose their mechanical advantage for resisting vertical shear.
Yep. So right when the architects need these beams the most, for those wide luxury floor plans, the diagonal reinforcement strategy becomes mathematically useless.
Wow. So conventional RC degrades, and diagonal RC becomes an unbuildable geometry-dependent mess.
Which pushes the industry towards steel.
And I find this pivot fascinating because it's such a blunt force solution. Like, if complicated rebar cages are failing us, let's just use a massive, solid steel, wide flange I-beam.
It really is the ultimate brute force engineering approach.
Can use it bare or encase it in concrete.
Yeah. And steel inherently possesses the ductility we are looking for. An encased steel composite beam can handle immense shear and bending moments.
But it introduces an entirely new catastrophic problem at the boundary conditions.
It does. To transfer the load from a steel I-beam into a reinforced concrete shear wall, the steel member must be deeply embedded into the wall pier.
Right, and we use models like the rigid Matic-Gaffar embedment theory to calculate that necessary anchorage length.
Exactly. And here's the clash.
I call it the structural traffic jam.
That's the perfect term for it. It is a severe detailing clash. The shear wall pier is not empty concrete.
Right, the edges of those walls are called boundary elements.
And they are packed with dense, large-diameter vertical rebar running continuously up the height of the building.
So when you try to shove a wide flange steel I-beam horizontally into that wall, the wide top and bottom flanges of the steel beam physically slam into the vertical wall rebar.
They absolutely do.
And you obviously can't cut the vertical rebar of your primary gravity and lateral resisting wall.
Never. That's a structural non-starter.
So what happens? How do they solve it?
The engineers are forced to pull the vertical boundary rebar further out, widening the ends of the shear walls to create space for the steel embedment.
Oh, wow. So this creates a barbell-shaped wall cross-section.
Exactly. And from an architectural perspective, creating bulging, thick wall ends at every doorway ruins the interior layout. It consumes highly valuable square footage.
The sources also point out a huge issue here for the MEP coordination, the mechanical, electrical, and plumbing systems.
Oh, right, the ceiling space.
Yeah, in a high-rise, the space directly below the ceiling slab is premium real estate for sprinkler mains, HVAC ducts, conduit.
And they often need to pass horizontally right through the zone occupied by the coupling beam.
Right. If you have a standard concrete beam, the contractor just drops a PVC sleeve into the formwork before the pour, and you have a perfect conduit hole.
But if you have a solid steel wide flange beam, the MEP contractor has to physically torch or drill through the heavy steel web while elevated on a scaffold.
Which is incredibly labor-intensive.
It's a safety hazard, too. And if they cut too close to the flanges, they can critically compromise the shear capacity of the beam.
All of this history, the failures, the rebar congestion, the barbell walls, it all perfectly sets the stage for the PRC beam.
The plate-reinforced composite coupling beam.
Yes. When you look at the anatomy of this thing, it's such an elegant synthesis of everything we've learned. How does it actually work?
Well, the concept is brilliantly simple. We abandon the 3D wide flange shape of the I-beam entirely. Instead, we take a single, thick, flat, two-dimensional steel plate. We orient it vertically, and we embed it dead center along the longitudinal axis of a conventional reinforced concrete beam.
So it's literally just a flat steel spine running through the middle of the concrete.
Exactly. And that specific geometry solves the wall connection clash instantly.
It completely eliminates the traffic jam.
Right. Because it is a flat vertical plate, it has no wide horizontal flanges.
So when it embeds into the shear wall, it simply slides right between the curtains of vertical boundary element rebar.
Yes, you don't have to cut any rebar,
Yeah.
and you don't have to widen the wall into a barbell shape.
That is so clever. And from a concrete rheology perspective, pouring around a vertical plate has to be infinitely better than pouring through a dense diagonal truss.
It's night and day. The wet concrete flows seamlessly down the smooth vertical faces of the steel plate.
So you get excellent consolidation with just standard vibration.
Exactly. Furthermore, the two materials inherently protect each other in this configuration.
How so?
Well, the concrete matrix completely encases the steel plate, providing exceptional fireproofing.
Right, because bare steel loses its yield strength rapidly at high temperatures.
Exactly. The concrete cover acts as a massive thermal mass.
But the concrete is doing more than just fireproofing, right? It's providing structural restraint against buckling.
Crucially, yes. If you put massive compressive stress on a relatively thin, deep steel plate, it will want to buckle out of plane laterally.
It'll just pop sideways.
Right. But in a PRC beam, the continuous concrete matrix acts as a rigid lateral brace along the entire length and depth of the plate.
So it forces the steel to reach its full yield stress rather than failing early through elastic buckling?
Precisely.
But we have to address the interface here, because if you just drop a smooth steel plate into wet concrete and let it cure, they aren't going to act compositely.
No, they wouldn't.
Under the cyclic stress of an earthquake, the concrete will crack, and that smooth steel plate will just slip right out of the matrix.
And that is the defining challenge of composite design, interface, shear transfer.
Right.
If the two materials slip independently, you just have two weak beams side by side. To make them act as a single, unified, deep beam, you have to mechanically lock them together.
And that is achieved using headed shear studs.
Exactly.
These are like heavy-duty metal rivets welded to the face of the plate.
Yep, they are high-strength steel shanks with a flattened head, and they are arc welded in specific grid patterns onto both sides of the vertical steel plate.
Before the rebar cage is even assembled, right?
Yeah, it's done in the fabrication shop.
I want to focus on the micromechanics of how those studs actually work when the building sways, because it's not just friction holding them together.
Not at all. When the beam undergoes shear and flexure, the steel plate tries to slip past the concrete.
Okay.
The shank of the headed stud acts as a rigid dowel. The concrete bears directly against the leading edge of that heavy steel shank.
So the stress concentrations right at the base of the stud must be immense.
They are.
The concrete is literally being crushed against the stud.
It is. It's localized compressive bearing. But the stud doesn't just act as a dowel. The flat head on the stud is critical here.
Why is the head so important?
As the plate tries to slip, it also tries to separate laterally from the concrete, an out-of-plane separation.
Oh, it tries to push away from the concrete.
Right. The flat head of the stud anchors deep into the concrete cover, resisting that pull-out force through what we call a compression cone mechanism.
So it ties the outer concrete shell firmly to the inner steel core.
It does. It's an incredibly robust connection.
And that brings us to the actual design methodology. We understand why the PRC beam exists and how it physically works, but how does an engineer actually sit down and draft one?
Well, it's not simple.
Right. The sources provide a rigorous four-part master design procedure developed by researcher R.K.L.
Yes, and it's heavily based on the structural demands of high-rises in regions like Hong Kong.
It's a very comprehensive methodology, and it establishes boundary conditions right away.
It does. This procedure is calibrated for practical coupling beams, where the span-to-depth ratio is between 1.0 and 4.0.
Okay.
Furthermore, the geometry of the steel plate itself is constrained. The depth of the steel plate should be between 80% and 95% of the total depth of the composite beam.
Wait, why that specific ratio? Why not just make the plate the exact same depth as the concrete?
Because you need top and bottom concrete cover for fire rating, first of all.
Oh, right.
And you also need physical space to run the top and bottom longitudinal rebar of the RC component without hitting the top edge of the steel plate.
Makes sense. So the plate takes up the maximum internal real estate possible while still respecting the cover boundaries.
Exactly.
Let's get into the math. Step 1 of Su's procedure is the estimation of ultimate shear capacity.
Right.
This is the absolute ceiling of what the beam can handle, and it's dictated by the concrete, not the steel.
Right. When we model the worst-case load combinations, dead load, live load, plus maximum seismic lateral force, we determine the ultimate design shear force, which we call VU.
Okay, VU.
The absolute first check is ensuring that this force does not simply pulverize the concrete matrix instantly.
Because if the concrete shatters, the beam is gone.
Exactly. Su's research establishes a hard upper limit for the maximum allowable shear stress of the entire composite section.
For grade 60 concrete, which is around 8,700 psi, highly common in modern towers, the cap is set at 12 megapascals.
12 MPI is an immense amount of shear stress.
It sounds like a lot.
It is, but the physics dictate that if the applied stress exceeds this value, the principal compressive struts within the concrete matrix will crush in a brittle manner.
Regardless of how much steel you have inside.
Exactly. The structural integrity of the surrounding matrix just collapses.
So if your VU generates stress over 12 MPI, you cannot solve it by thickening the steel plate.
No, you can't. You have to go back to the architect and increase the overall physical dimensions of the beam itself.
Wow. Okay, so provided we are safely under that 12 MPI limit, we move to step 2.
Designing the RC component and the steel plate.
This is where we allocate the load between the two materials.
Right, the load sharing mechanism. We calculate the allowable shear capacity of the reinforced concrete component on its own. We call this VRC, allo.
And this includes the concrete's contribution plus the capacity of the conventional vertical stirrups we are still placing around the plate, right?
Yes, exactly. We subtract that from the total VU to find out how much shear force is left over.
Okay, basic math so far.
Right. That remaining force is the required shear capacity of the steel plate, V freak.
But there is a massive caveat here. You can't just let the steel plate take whatever load is left over.
No, you can't.
The sources impose a strict limitation. The steel plate must not carry more than 45% of the total ultimate shear force.
The equation is V freak is less than or equal to 0.45 V.
Wait, I need to push back on this.
Go ahead.
We are embedding a highly ductile, extremely strong, custom-welded plate of structural steel into this beam. Why handicap it at 45%?
It does seem counterintuitive.
Right. If the steel can handle 70% of the load, why not let it? Aren't we leaving structural capacity on the table?
It's a great question, but it's really about deformation harmony.
Deformation harmony.
Yes. Remember, this is a composite member. The steel plate and the concrete matrix are locked together by the shear studs. They must share the same strain profile.
Okay, they have to move together.
Exactly. If you force the steel plate to carry, say, 70% of the massive shear load, the steel plate will undergo significant elastic and then plastic deformation.
The steel stretches and twists.
Yes. The steel can survive that high strain, but the concrete encasing it cannot.
Oh.
If the steel plate undergoes massive deformation to carry that 70% load, it drags the surrounding concrete along with it.
And the concrete will just crack.
It will suffer severe, unrepairable cracking and catastrophic spalling long before the steel plate reaches its ultimate limit state.
I see. By capping the steel plate share at 45%, we ensure that the stiffness and the yielding of both materials degrade at a complementary rate.
Exactly. It preserves the integrity of the concrete cover and maximizes the global ductility of the entire system.
That makes perfect sense. The strong material has to pace itself so it doesn't shatter the brittle material it's wearing.
That's a great way to put it.
Okay, so once we verify the load share is under 45%, we have to calculate the actual thickness of the steel plate.
And Sue's methodology forces a critical fork in the road right here.
Right, depending on whether it's a low shear load or a high shear load scenario.
Yes, and this distinction is entirely based on the span-to-depth ratio we discussed earlier. The boundary line is a ratio of 1.5.
Okay, so if the span-to-depth ratio is less than 1.5, meaning a short, stubby beam, it falls under high shear load.
Right. These beams are incredibly stiff dynamically. Under lateral sway, they don't really bend. Instead, the extreme forces try to guillotine them right at the wall interface.
So they are shear controlled.
Yes. Therefore, the required plate thickness is calculated purely based on the ultimate shear force.
But if the span-to-depth ratio is 1.5 or greater, which is most architectural corridors, it falls under low shear load.
Correct. And this means the beam is flexure controlled. It's going to bend.
And analyzing the bending of this composite beam reveals some incredibly complex mechanics, particularly regarding the neutral axis and internal axial forces.
Oh, this is where standard RC beam theory completely breaks down.
How so?
Well, in a normal concrete beam subjected to pure bending, one side is in tension, the other is in compression, and the neutral axis, the plane of zero strain, sits somewhere in the middle.
Right, standard beam bending.
But a PRC beam is not standard. Because of the heavy steel plate and the shear stud interaction, the flexural behavior at the critical beam wall joint generates unique internal boundary conditions.
Let's trace the mechanics of that. As the building sways, the beam is subjected to a massive bending moment at the wall joint.
Yes.
The top of the beam might be stretching in tension while the bottom is squishing in compression.
Yes, and because the steel plate and the RC section have different stiffnesses and different yield points, they inherently want to adopt different curvature profiles.
But the shear studs force them to adopt the same curvature.
Exactly. This forced composite action induces equal and opposite horizontal longitudinal forces on the RC part and the steel plate.
The equations represent this as a net compressive force on the RC component, denoted as X.
Exactly. The interaction literally squeezes the reinforced concrete component axially while it's trying to bend.
Oh, wow.
Because of this induced axial compression, the location of the neutral axis for the RC section shifts dramatically.
So you cannot assume a simple rectangular stress block based on pure flexure.
No, you can't. The engineer must go through a rigorous iterative calculation to locate the new neutral axis depth.
Taking into account the yield strain of the longitudinal rebar and the specific induced compressive force Fx.
It's an intense balancing act. You calculate the moment capacity of the RC section under that specific axial load, and you add it to the moment capacity of the steel plate.
And the combined total must be greater than your ultimate design moment mood.
Right. That allows you to solve for your required plate thickness and your required longitudinal rebar area simultaneously.
It highlights why PRC design is so highly specialized. The materials are constantly reacting to one another's localized stiffness.
Very much so.
Okay, so we've sized the steel plate, we know the concrete dimensions, and we know our rebar. Now we move to step 3.
Step-by-step shear stud arrangement.
We know the studs are the mechanical link, but how do we actually map them out? In finite element models for standard composite members, you often see a uniform distribution to prevent localized stress concentrations.
Right.
Do we just blanket the plate in studs?
We do not. Blanketing the plate is highly inefficient and creates poring issues.
Okay.
Su's research, utilizing extensive finite element analysis and experimental testing, categorizes the required shear studs into 4 distinct functional roles.
And mapped across 5 specific geometric regions of the plate, right?
Yes. Let's break down those 4 functions.
What exactly are the studs doing?
Function 1. Vertical studs for inducing shear. These are responsible for transferring the primary vertical shear force from the concrete into the steel plate.
So they are critical at the beam ends.
Exactly. Function 2. Vertical studs for the tension tie effect. This is the confinement mechanism.
How does that work?
As the beam bends, the massive diagonal compressive struts in the concrete tend to push outward, trying to separate the top and bottom concrete cover from the steel plate.
Ah.
These studs act like a mechanical zipper, tying the top and bottom edges of the plate to the extreme concrete fibers.
That's a great visual. A metal zipper. Okay, what about function 3?
Function 3. Horizontal studs for inducing moment. These transfer the longitudinal shear flow generated by the flexural bending.
Okay.
And function 4. Horizontal studs for inducing axial force. These specifically handle the transfer of that induced 5x compressive force we just talked about.
4 complex load paths. How does that translate to the physical map of the 5 regions?
Well, picture the rectangular steel plate spanning between the 2 walls.
Okay, I'm picturing it.
Region I and Region 2 are the extreme left and right vertical ends of the plate, exactly where the beam meets the wall joints.
Got it.
The width of these regions is precisely defined as 0.3 times the depth of the plate. This is the high-stress zone. You pack studs densely here to handle function 1, that massive vertical shear transfer.
So the vertical edges are heavily armored.
Yes. Then, region 3 and region 4 are horizontal strips running along the very top and very bottom edges of the plate, bridging the 2 end regions.
And this is where you locate the studs for function 2, the tension tie zipper, as well as the horizontal transfer for functions 3 and 4.
Exactly.
Okay, so that covers the perimeter. Left, right, top, bottom. That leaves region V, the vast, dead center of the steel plate's web.
And here is the defining optimization of Su's methodology. Region V is left completely blank. 0 shear studs.
Wait, hold on. You just said that the studs force the 2 materials to share the same curvature. Why would you leave a massive void right in the center of the web where the plate is deepest?
It comes down to analyzing the shear flow at the material interface.
Oh.
Finite element models track exactly how the stress moves between the concrete and the steel. The stress transfer naturally concentrates at the boundaries, the extreme fiber interfaces, and the rigid wall joints.
Oh, I see.
The center of the plate, region V, sits adjacent to the neutral axis of these shear transfer mechanisms. During an earthquake, the relative slip between the concrete and the steel in the dead center of the plate is practically 0.
Wow. If there's no slip, there's no force transfer.
Exactly. If you weld 50 studs into the center of the plate, they won't be mobilized. They will carry 0 load.
So it is a complete waste of material and welding labor.
Yes, and worse, it unnecessarily clutters the center of the plate, impeding the flow of the wet concrete during the pour.
By leaving region V blank, you optimize the material usage and solve the construction rheology problem simultaneously.
It's beautiful engineering, honestly. Don't armor the area that doesn't seek combat.
Now, there is a major penalty applied to these studs in the math, isn't there? The 60% rule.
Yes, there is. When calculating the required number of studs for all those regions, we use a characteristic resistance capacity for each stud, called Q.
Right.
But the code strictly mandates that we assume the studs only achieve 60% of their theoretical capacity. We use 0.6 QK in every equation.
Why such a massive reduction factor? If the stud is rated for a certain load, why only trust it to 60%?
It's due to the kinematic boundary conditions of a vertical coupling beam compared to a horizontal floor beam.
Okay, break that down for me.
In a standard composite floor system, like a horizontal steel beam under a concrete slab, when it undergoes bending, it deflects downwards freely.
Right, it sags.
Exactly. That massive deflection creates massive interfacial slip between the steel and the concrete. That large slip highly mobilizes the shear studs, pushing them to their ultimate capacity.
But our beam is vertical.
And it is pinned between two infinitely stiff shear walls that are heavily loaded in axial compression from the gravity of the 50 stories above them.
Oh, wow.
The PRC coupling beam is kinematically confined. Because it cannot freely expand or deflect in the same way a floor slab can, the actual physical slip between the plate and the concrete is highly constrained.
So because the slip is so small, the studs never get stretched to their ultimate limit before the concrete itself begins to yield in other ways.
Precisely. The studs simply cannot reach 100% mobilization in this specific vertical confined geometry. The 0.6 factor is a heavily researched calibration to reflect the reality of that restricted slip strain.
Okay, so we have the beam span mapped out. Step 4 is the final piece of the procedure, design of plate anchorage in wall piers.
Right.
We solved the traffic jam by using a flat plate, but that plate still has to lock into the wall somehow.
The beam is only as strong as its boundary connection. The steel plate must extend deeply into the concrete wall pier.
And that embedment depth is the anchorage length, Liao.
Yes, and the forces trying to rip that plate out of the wall are staggering.
I can imagine. It's basically a massive crowbar.
That's a very good way to look at it. We use a simplified plate anchorage design model. The anchor portion of the plate must resist 3 massive force components.
What's the first one?
First, the ultimate plate moment, the rotational prying force trying to twist the plate out of the concrete.
Makes sense.
Second, it must resist a huge percentage of the ultimate plate shear. Parametric studies indicate that the anchor portion handles between 50% to 75% of the total plate shear force, with the rest distributed along the beam span.
Wow, up to 75% and the third force.
Third, it must resist that horizontal axial force, Finx.
And we use the exact same shear studs inside the wall anchor to transfer these forces.
We do. And just like the beam span, the anchor is divided into bearing stress regions. Region the first of the anchor is the vertical strip immediately adjacent to the beam wall joint.
Okay.
Region 2 extends deeper into the core of the boundary element. You calculate the required number of studs to resist the combined moment, shear, and axial forces.
But there's a very strict spatial limitation inside the wall, isn't there?
The minimum spacing rule, yes. The code dictates that the spacing between individual shear studs must be at least 5 times the nominal shank diameter of the stud.
Okay, but what if the math says I need 50 studs, but I don't have the surface area to place them 5 diameters apart? What happens? Why can't I just pack them tighter?
Because of the compression cone mechanism we discussed earlier.
Oh, right.
When the stud transfers load, it exerts a massive localized compressive bearing stress on the concrete around it, radiating outward in a cone shape.
Right, the pull-out resistance.
Exactly. If you place the studs too close together, those highly stressed compression cones overlap. The combined outward radial pressure acts like a wedge, and it will violently burst the surrounding concrete matrix apart long before the steel plate yields.
You lose all anchorage instantly.
Yep. If you can't meet the minimum spacing, you must increase the anchorage length, lie, driving the plate deeper into the wall to gain more surface area.
That covers the theory, the 4-part methodology. Let's take all of this dense math and apply it to a real-world scenario.
Okay, let's do it.
Part 4 of our deep dive. Let's walk through the specific design example provided in the source material to see how this harmonizes.
Let's set the architectural parameters first. We're designing a PRC beam over a corridor in a high-rise.
Okay.
The clear span of the beam is 2 meters. The width is 250 millimeters, matching a standard 10-inch shear wall above and below it. The total depth of the beam is 500 millimeters.
So span of 2 meters, depth of 500 millimeters, that gives us a span-to-depth ratio of exactly 4.0.
Which means this solidly qualifies as a low shear load beam. It is flexure controlled.
Right.
The structural analysis software, your ETABS or SFP 2000 models, has run the seismic load combinations, and it gives us our ultimate design forces. The ultimate shear, VU, is 800 kilonewtons. The ultimate moment, mu, is 800 kilonewton meters.
And the materials specified are grade 40 concrete, high-yield T40 longitudinal rebars, and grade S355 structural steel for the plate.
Perfect. Step 1. Check the shear limit. Will 800 kilonewtons shear crush the grade 40 concrete?
Let's see. We run the calculation, and the nominal shear stress comes out to 7.3 megapascals.
And the maximum allowable cap for grade 40 concrete under Sue's formula is roughly 9.48 MPa.
So since 7.3 is less than 9.48, the concrete matrix will survive the compressive strut forces. We proceed.
Exactly. Step 2. The load sharing. How much of that 800 kilon is the reinforced concrete taking, and how much is left over for the plate?
Right. The standard concrete equations, accounting for the vertical stirrups, tell us the RC component can safely handle an allowable shear VRC allow of 492 kN.
That means the steel plate must carry the remainder. 800 minus 492 gives us a required plate shear capacity, VPREC, of 308 kN.
But we have to hit the golden rule check. Is 308 kN less than 45% of the total 800 kN?
Well, 45% of 800 is 360 kN.
And since 308 is less than 360, we are not overstressing the steel relative to the concrete. The deformation harmony is maintained.
Exactly. Now, we size the plate. The beam depth is 500 millimeter. To respect the 0.8 to 0.95 geometric ratio rule for concrete cover, the engineer selects a steel plate depth of 400 millimeter.
That gives a ratio of 0.8. Perfect.
Because it's a long beam governed by bending, we have to run those intense neutral axis equations to find the required thickness, factoring in the x-axial compression.
Skipping the iterative algebra for time, the calculations demand a steel plate thickness of 25 millimeters.
Right, so our core element is defined. A flat plate, 2 meters long, 400 millimeters high, and 25 millimeters thick.
Step 3. Mapping the shear studs. The engineer calculates the forces for all 4 functions and applies the 0.6 QK reduction factor. What does the final blueprint look like for the beam span? We are using standard 16 millimeter diameter headed studs.
The output is incredibly precise. In regions 1 and 2, the vertical ends near the wall, they only need 2 studs per column on each side of the plate.
Wow, that seems remarkably low for the high-stress shear zone.
It is, but remember, this is a long flexure-controlled beam. The massive bending moments are the primary driver, not the sheer slicing force.
Oh, okay.
That reality is reflected in regions the 34, the top and bottom horizontal edges. To maintain the tension tie and transfer the longitudinal moment forces, the engineer must place 7 studs in a row along the top edge and 7 studs along the bottom edge on both sides of the plate.
And region V, the center web, is left as bare steel.
Exactly. Step 4, the anchor. We must embed this 25 millimeter thick plate into the shear wall piers. The calculations dictate a minimum anchorage length, law, of 900 millimeter.
Nearly a meter of plate pushed into the boundary element on both sides, and inside that wall, the stud density just explodes.
Because it has to resist that massive prying moment. In region 1 of the anchor, right near the joint, the math requires 4 studs per column.
Okay.
But deeper into the wall, in region 6 of the anchor, the leverage forces dictate a massive array. 40 studs arranged in 10 columns of 4 on each side of the plate.
It's an incredible visualization. A heavy steel spine spanning the corridor, a scattering of studs at the visible ends, a tight zipper of studs along the top and bottom edges, an entirely blank center, and then hidden deep inside the concrete walls, absolute thickets of dozens of studs locking the plate into the global lateral system. It proves how highly calibrated the force transfer is.
It really is the antithesis of the brute force I-beam approach. It is surgical engineering.
Which brings us to the final summation. For the structural engineers actually signing off on these drawings, what are the absolute hard stops?
The rules of thumb.
Exactly. The sources provide a highly consolidated engineer's compliance checklist based on the intersection of SU's methodology and local building codes. Let's run through them quickly.
If you are the engineer of record, there are 6 non-negotiable checks. Rule number 1, the geometry check.
Right.
The depth of the steel plate must be between 80% and 95% of the overall composite beam depth. It's outside this window, you either lack sufficient flexural engagement or you lack adequate fire cover.
Rule number 2, the span check.
The span-to-depth ratio of the beam must be between 1.0 and 4.0. If you have an ultra-deep, incredibly short beam, the flexural equations break down entirely, and it acts purely as a deep shear friction element.
And if it's over 4.0?
It acts like a normal floor beam, and the composite assumptions regarding the fist axial force are no longer valid.
Okay, rule number 3, the shear cap.
The absolute maximum nominal shear stress of the composite section must not exceed 1.5 times the square root of Q in megapascals. This is the hard ceiling to prevent catastrophic, brittle crushing of the concrete compressive struts.
Rule number 4, the load sharing limit.
The steel plate must never be assigned more than 45% of the total ultimate shear load. Exceeding this ensures the concrete matrix will spall and fail before the steel yields, destroying the ductility of the element.
Rule number 5, the embedment check.
The physical anchorage length extending into the wall pier must be carefully detailed, and practically it usually falls between 0.35 and 0.7 times the clear span of the beam to provide enough surface area for the internal anchor studs.
And finally, rule number 6. This one fascinates me because it bridges the gap between physical reality and digital simulation. the stiffness reduction check.
This is critical. When you build the 3D computer model of the skyscraper in structural analysis software, you are typically using elastic models. But we know that during a major seismic event, the building will not remain perfectly elastic. The concrete in the coupling beams will crack. The rebars will experience minor slip. The fixity at the wall joint will yield slightly.
If you don't account for that, the computer thinks the building is much stiffer than it actually will be. It will underestimate the drift.
Which is a potentially fatal miscalculation.
Yeah.
Therefore, the code mandates that the engineer manually reduce the effective bending stiffness of the modeled PRC beams.
How much do they reduce it?
Su's methodology, aligning with standard practices, recommends modifying the moment of inertia. You apply a stiffness modifier, effectively reducing the beam's rigidity to 35% of its gross uncracked section.
We write this as 0.35 ECIG.
You are quite literally programming the assumed damage and yielding into the simulation so that the global building drift calculations reflect reality.
You have to assume the cartilage will flex to understand how far the bones will sway.
That's exactly it.
It's a perfect synthesis of theory and practical modeling. When you pull back and look at the entire deep dive, the PRC coupling beam is a masterclass in lateral thinking.
It truly is.
The industry was stuck. Conventional concrete pulverized itself. Diagonal rebar cages were a nightmare of congestion and honeycombing. Steel I-beams created impossible traffic jams with the wall reinforcement.
And the solution wasn't discovering a new, exotic supermaterial. It was simply taking a standard structural shape, flattening it from 3D to 2D, and meticulously studying the interfacial shear mechanics to understand exactly where to place those headed studs.
It retains the fast, clean construction of a conventional rectangular beam, avoids the clashing of the boundary elements, and achieves the massive life-saving ductility required for extreme seismic zones.
It really shifts your perspective. The next time you are walking down the corridor of a super tall building, maybe heading to a corner office or stepping out of an elevator lobby, take a second to look up at the doorway headers.
Yeah, you are likely walking right underneath one of these intensely engineered hybrid components. A 2-inch thick plate of steel, meticulously mapped with hundreds of hidden metal studs, silently confined inside a matrix of concrete.
Waiting to keep the tower standing when the Earth decides to move. It's the hidden anatomy of the modern skyline.
And it leaves me with one final provocative thought. If we can radically optimize a building's energy dissipation and solve massive physical construction bottlenecks simply by taking a bulky 3D steel member, flattening it into a 2D plate, mapping out the specific shear flow interfaces with studs, and embedding it vertically inside a concrete matrix, what other rigid infrastructure could this apply to?
That's a great question.
Think about heavy civil engineering, bridges, hydroelectric dams, deep subterranean tunnel linings. Could we completely revolutionize those massive, hard-to-build, rebar-congested structures by hybridizing materials in this highly targeted plate and matrix way? Could optimizing interface slip be the fundamental key to unlocking the ultra-lightweight, perfectly earthquake-proof mega-cities of the next century?
It's certainly possible.
It's something to think about the next time you feel the wind push against the glass.